This video will look at the basic principles of heredity, focusing in on using probability to solve genetic problems. So the use of probability is very important in genetics. Probability is simply the likelihood of a certain event occurring, and we're going to use it in genetics to predict the outcome of genetic crosses. So we're going to focus on two probability rules. First of all, the multiplication rule. This is also called the product rule. And second is the addition rule, also called the sum rule. Let's start with the multiplication rule. This rule states that the probability of two or more independent events occurring together is simply calculated by multiplying their independent probabilities together. So the example here uses a die, and the question is, if you roll a die 2 times, what is the probability that you get a 4 on both rolls? So we all know that the chance of getting a 4 on one roll, there's 6 possibilities, so the chance of getting a 4 is 1 out of 6. That would be roll 1. Same thing with roll 2. The chance of getting a 4 when you roll a die is 1 out of 6. Now the question asks, what's the probability of getting a 4 on both rolls? And so if we need both of those things to be true, we're simply going to multiply those two probabilities together, 1/6 times 1/6 to get 1/36. I'd like to go through two other examples that use the multiplication rule. The first one is a question: if you toss 3 coins, what's the probability that all 3 of those coins will show heads? So in this case, we're going to have coin 1, coin 2, and coin 3. The chance of getting heads with coin 1 is 1/2. Chance of getting heads with coin 2 is also 1/2. Chance of getting it with coin 3 is also 1/2. So in this case, we have 3 independent probabilities, and the question is asking whether they all are true. So the chance that they all happen together is going to be calculated by multiplying those individual probabilities together to give 1/8. In the second question, Jane and Eric are both heterozygous for the recessive cystic fibrosis mutation. And so if they have a child together, the chances of having an affected child who has cystic fibrosis is 1 in 4. The question actually asks, if they have 2 children, what's the chance that both will have cystic fibrosis? And so we're going to look at child 1 and child 2. Chance that child 1 will have cystic fibrosis is 1/4. Same probability for the second child. Since these both need to be true, we're going to multiply them together to get 1/16. I'd like to also have you use probability in solving things that in the past we've used complex Punnett squares for. So if you remember, when we looked at Mendel's dihybrid cross, when we got to the F2 generation, we were obliged to make this very complicated 4x4 Punnett square. So what about if you have 3 genes, or even 4 or 5 genes? Once we get to that point, it really becomes impossible to calculate probabilities based on a Punnett square. And so I'd like to teach you how to use probabilities to solve problems. So we're going to use probabilities to solve this result of Mendel's dihybrid cross, where we get this result of 9 to 3 to 3 to 1. So this approach uses something called a branch diagram. A branch diagram relies on the fact that those 2 genes are really separate from each other. And so when Mendel did a cross with round versus wrinkled and yellow versus green, those were 2 independent 3 to 1 ratios that were observed. So when we do a branch diagram, we just look at one gene at a time. And so first we look at the round versus wrinkled result, and we find in the F2 generation that 3/4 of those will be round, which is the dominant phenotype, and 1/4 are wrinkled. Now, since the second trait, yellow versus green, is independent of the first trait, of those 3/4 that are round, 3/4 of those will be yellow and 1/4 of those will be green, again because yellow is the dominant trait. Same thing with the wrinkled. Of those 1/4 that are wrinkled, 3/4 of those will be yellow and 1/4 will be green. Now, in order to solve this problem, Using the multiplication rule, we just have to multiply through. So if we'd like to know the ratio of progeny that are both round and yellow, we're going to multiply through, multiply 3/4 times 3/4, and that's going to give us 9/16. If we'd like to know the proportion that are round and green, we're going to multiply through again, 3/4 round times 1/4 green, that's going to give us 3/16. And this can be continued on, and we end up with this 9:3 to 3:1 ratio that we previously found using the standard Punnett square approach. Now, I won't lie, the branch diagram does tend to get really complicated when you get a lot of genes that you're considering. But we can use this approach to very easily answer more directed questions. So here is a cross between two hybrids looking at 5 different genes. And the question is, what is the probability of getting all recessive traits in this cross? Now this looks really tough if you're thinking about doing a Punnett square, but using probabilities it's actually quite easy. So we start off by looking at just one gene at a time. So you look at this cross between the two A genes, and the chance of getting little a is 1/4. Same thing with the B gene. Chance of getting little b with the cross between two heterozygotes is 1/4. And same thing with C, same thing with D, and same thing with E. Since we need all these things to be true, we have to be recessive for all 5 genes. We're going to multiply those individual probabilities together, and that will give us 1 out of 1024. Let's talk about the addition rule next. So you're going to use the addition rule when there are multiple ways to satisfy a criteria that is set forth in a problem. And each of those individual events has its own probability associated with it. So the example we're going to look at here is rolling one die one time, and the question is, what is the chance of getting a 3 or a 4? So the chance of getting a 3 we know is 1/6. The chance of getting a 4 is 1/6. And if either of those two scenarios is able to satisfy your criteria, then we're going to add those two probabilities together. 1/6 plus 1/6 equals 1/3. So I'd like to solve 2 problems using the addition rule. So sometimes these problems can get a little bit tricky, and so I set out 3 steps of how to solve problems using these addition rules. So the 3 steps are, first, to list all the possible ways to satisfy the criteria in the problem. Second, to calculate the probability of each way. And then number 3, you add those probabilities together. So the first question here is very simple, and we should be able to answer this with no trouble, just logically. So in a monohybrid cross between 2 heterozygotes, what's the probability that an offspring will be homozygous? So we know that there are actually 2 ways that you can satisfy this criteria, right here and right here. And so we're going to use these 3 steps. First of all, we're going to list the ways to satisfy those criteria. So the first way would be to be big A, and the second way would be to be little a. Next, we're going to calculate the probability of each of those 2 ways to satisfy the problem. And so chance of being big A is 1/4. Chance of being little a is also 1/4. Third step is we're going to add those probabilities together, because either one of those can satisfy the criteria in the problem. And so we're going to add those together. We get 2/4 or 1/2. This second problem is a little bit more tricky. So Jane and Eric are both heterozygous for the recessive cystic fibrosis mutation, and the question is, if they have 2 children, what is the chance that no more than one of their children will have cystic fibrosis? So first we have to consider, what's the probability of having a child with cystic fibrosis? And if they're both heterozygotes, that answer is going to be 1/4. And the chance of having a child without cystic fibrosis is going to be 3/4. So we're going to consider child 1 and child 2. First thing we'll do is list all of the possible ways to satisfy the criteria that is set out in the problem. So one possible way to have no more than one child with cystic fibrosis is to actually have none. Okay, so that would be first child doesn't have it, second child doesn't have it. Another way would be to have the first child have cystic fibrosis and the second child no. And the third and final way would be for the first child not to have cystic fibrosis and the second child to have it. Okay, next we're going to calculate the probability of each of these individual scenarios. So this first scenario, let's put the probabilities in. The chance of having a child who does not have cystic fibrosis is going to be 3/4. Same thing with the second one, and we're going to calculate that overall probability by multiplying these two probabilities together. Chance of the second scenario, a child with cystic fibrosis, 1/4, no is 3/4. And so we're going to multiply those two probabilities together to get 3/16. And then the final one is the same as the second one, just flipped around here. It also gives a probability of 3/16. The final step is to add the overall probabilities together. And so the reason, again, why we add these probabilities together is because any of those three can satisfy the criteria that is set out in the problem. And so the final answer would be 15/16. So to summarize these two probability rules, the multiplication rule is used when you need both events to happen. So these multiple events with their own individual probabilities must all occur. And so we often call this the AND rule because event A and event B must occur, and so that is when you multiply. For the addition rule, there are several ways that you can satisfy the criteria that is outlined in the problem. And so we call this the OR rule often. So either A or event B can satisfy that criteria, and that OR is the signal that you should add those two probabilities together using the addition rule.